Okay, so we're moving on to section 4.2, and we're going to talk about exponential functions. So exponential functions, well, it's a type of function, one that you probably are not familiar with, one that hasn't really come up yet very often. And so let's sort of start with this first example here. Just to show you sort of the power of exponential functions. So let's suppose you win a certain type of lottery, and you have two choices, right? They can either pay you $1 million, where, you know, a lot of people would take that, or they can pay you 1 penny the first day, right? 2 pennies on the second day, 4 pennies on the third day, right? And then they double the number of pennies every day for the next 30 days. Okay, so you're talking about pennies here, right? So on the fifth day would be, on the fourth day would be 8 pennies, right? On the fifth day would be 16 pennies. So you're thinking, okay, that's just pennies. I'd rather have the $1 million. Well, okay, but as it turns out, option B is way better, right? If you're given the choice, I would pick option B, right? So yeah, it doesn't seem likely because you're just talking about pennies here. But remember, you're doing this for 30 days. So after the 30th day, you're going to end up with, right? So for option B, you're going to end up with approximately $10,737,418 and I think exactly 23 cents. So, yeah. So if you pick the $1 million, you're essentially leaving more than $9 million on the table, almost $10 million, right? So, yeah. So $9.7 million. Yep. Say goodbye to that. So you have to think about this a little bit, right? A lot of people probably would end up taking the $1 million because they couldn't possibly think that option B is more money, and it turns out it is. And that's the power of exponential functions. Exponential functions grow very quickly. So when you double every day, it doesn't take that long. It only takes about a month. In fact, it probably takes somewhere around 22, 23 days to get the $1 million. Actually, I want to say more like 25 or 26 days to get to the $1 million. But right after 30 days, you get to 10 million. You get way more. So that's the power of exponential functions. Okay, so what is an exponential function, right? An exponential function, it's sort of in its basic form. The basic form of an exponential function just looks like this, right? So you have f of x, because it is a function. It's just going to be some number. I'm going to call that number b for now, raised to the power x. Okay? So yeah, don't get confused with functions that we've seen before, right? Like x cubed or x squared. These are not exponential functions. These are not exponential functions. I mean, you might think, well, wait a minute. Of course it's right? 2 is the exponent. 3 is the exponent. These are exponents. Well, that's true, but look at where x is. X is in the base, right? The exponents are just numbers. So notice that here, x is now in the exponent. Right? So when your variable is in the exponent, that's what makes it an exponential function. Right? Yep. So when you have something like f of x equals 2 to the x, right? That's what makes it exponential. Right? So not x to the 2, but 2 to the x. Okay? So what do we call these then? These are sometimes just called power functions, right? You can think of it as, x to the power 2, x to the power 3. So they're power functions, but they're not exponential functions, right? Right. Okay, so I should specify, of course, that this b here cannot be just any number. In particular, b has to be a positive number, right? So it doesn't make sense to take, say, -2 to the power x, right? It also doesn't make sense to take 1 to the x, because 1 to the x is just 1, and that's just a constant. Right? It's a horizontal line. So that's not an exponential function. So b has to be positive, but it cannot be equal to 1. So any positive number that's not 1 is allowed, right? So you can have an exponential function like 1/3 to the power x. Right? 1/3 is your b here. That's your, we call this the base, right? The base is just 1/3, so it is a positive number, and it's not equal to 1. So this is a perfectly good exponential function. Right? And in fact, there's another way you can write this. You can also write this as, well, 3 to the -x. And I'll let you think about that for a second, right? If you remember, 1/3 is just 3 to the -1. So that's just a different way to write it. Okay. So, right, so that's what exponential functions are, or what, that's their basic form of an exponential function. Now, x, right, what can the exponent be, right? So let's go back over here. Suppose we have f of x, it's equal to b to the x, right? What can x be? So that's its domain. What am I allowed to plug into the exponent? And surprisingly, you can plug in any number you want. The domain is all real numbers, right? So that includes negative numbers. Well, we know what a negative exponent is, right? It's just the reciprocal, right? So yeah, it could be negative, positive. It could be fractions or decimals, and so x can be any real number. However, the range is not all real numbers. b to the x is naturally going to be a positive number. Right? It cannot be negative. And it cannot be 0 either. Right? So b to the x will always be greater than 0. So no bracket here. You don't, there's no equal sign. You don't include, right? Don't include 0 here. Okay? Okay. So that's the domain and range of the exponential function. Right? And so to get the idea of what these functions look like, we should look at the graph. So I'm actually going to graph, in this case, fairly carefully what this function 2 to the x looks like. Okay, so yep, I'm going to bring up a little piece of graph paper here to make it easier to graph. So we're going to graph y equals 2 to the x, right? And how do you graph a function that, well, you've never seen before, so you don't know what it looks like? Just make a table, right? Plug in numbers, right? What if we plug in 0, right? What's 2 to the 0? Okay, it's not 0. All right, a lot of people would guess 0 here, but it's actually 1. Anything to the 0, right, is going to be 1. Well, anything except 0, right? A cannot be 0. So you cannot take 0 to the 0. That's just not a number. It's undefined. It's like dividing by 0. It's just not allowed. But 2 to the 0 is just equal to 1. Okay, so we're going to plot the point 0, 1. In fact, that's the y-intercept, so that's right about here. All right. Let's keep going. Let's plug in 1. 2 to the 1 is just 2. So we'll plot the point 1, 2. Right? We did 0, 1 already. 1, 2. 2 squared is 4. So we have the point 2, 4. And then 2 to the 3 would be 8. So that's 3, 8. And if we plug in 4, we're going to get 2 to the 4th is 16, which is off the scale here. So we might as well just end it here. So we'll plot these points here. So yep, 1, 2, right about here, 2, 4, and 3, 8 way up here. So when you connect the dots, you can see this does indeed increase very quickly. Right? Now remember, x can be, right, the domain is all real numbers, so I can plug in negative numbers, right? What's 2 to the -1? Not negative 2, right? Remember, negative exponent means take the reciprocal, so this is 1/2. So negative 1, 1 over 2. If you plug in negative 2, I got to squeeze that in here. We get 1 over 2 to the positive 2, which is 1 over 4. So negative 2, 1/4. And that's probably as much as we can do here. So, yep, when x is negative 1, y is 1/2. When x is negative 2, y is 1/4. When x is negative 3, it's 1/8. So what you're going to get here is essentially very, very small positive numbers, just a hair above the x-axis. So something like this, right? That's actually a pretty good graph. It helps to have graph paper, obviously. So, yep, this is the graph of y equals 2 to the x, right? Or I should say f of x equals 2 to the x, right? Because it is a function. It satisfies the vertical line test and so on. 2 to the x. Okay. So that's a pretty good graph here, right? Yeah, let's do one more. Let's do, how about g of x equals 1/2 to the x? So I'm going to do this by using a clever trick here, right? Remember, 1/2 to the x is the same as 2 to the negative x. So what happens when you change x to negative x? You just flip it over, right, the y-axis. So let's see if I can graph 2 to the negative x here. So if I flip this over, it's going to look something like this. And then, yep, just the mirror image. Ooh, I missed. Okay, that's too sloppy here. Let's try that again. I missed again. All right, I'll get it right. Oh, that's even worse. Boy, this pen, this stylus is not... You know what? All right, hang on. I'm going to work downward here. No, that's not... All right. Let's try one last time here. Oh, that's better. That's better. Okay, little squiggly here, but whatever. That's as good as I'm going to get here. Right, this should obviously not squiggle as much here. This should be pretty straight. All right, give me one more chance. Oh, boy, this is not working, is it? All right. See, okay. You're just going to have to settle for a bad graph here. Anyways, yep, so that's going to be g of x, which is 2 to the negative x, right? It's also 1/2 to the positive x. So the point that I wanted to make here is that when your a is less than 1, right, you're not going up, you're going down, right? So a to the x, right, is going to be increasing. It's going up if a is bigger than 1. And for this blue graph here, a to the x is going to be a decreasing function, right, if a is less than 1. Right? Now remember, a still has to be, oh, I'm sorry. Well, okay. In this case, it's a instead of b. Right? Remember, the base a here has to be greater than 0 anyways. Right? So I should have used a b here instead of an a, but you know, it's just a different letter. It's still the base, right? A is the base here. So a is the base, right? And x is the exponent. That's what makes it exponential. Okay, so the next thing I want to note here is that when you look at each graph individually, right, any horizontal line crosses the graph just once. So both of these functions, right, are just 1 to 1. Now, be careful, right? These are two separate graphs. So if it looks like my graph crosses twice, it doesn't, because these are two different functions, right? So yes, if I erase the blue graph, the black graph, the original function, everywhere only crosses just once, right? So in other words, and this is true for any b here, I'll go back to b, right? Your f of x, b to the x, is 1 to 1. So all exponential functions of this form are 1 to 1. Okay. So what that means is, right, every y comes from only one x. So if I have, say, b to the m and b to the n, the only way that can happen is if m equals n. Okay, and this actually works both ways, of course, but we're going to concentrate on going this way. Right, so in other words, if the bases are equal, the exponents have to be equal as well, right? And this is a very powerful statement. It actually allows us to solve some very simple equations. So suppose we want to solve the equation, how about 3 to the x is equal to 81? Okay. Now be careful. You're not just dividing by 3, right? The answer is not 27, right? So this is not 3 times x equals 81, right? In that case, you just divide by 3, and you get 27. But that's not the answer here, right? Remember, because x is in the exponent, right? So this is something we're gonna do a little bit later after test 3. We're going to learn how to solve equations like this in general. But in this case, I think we can do it fairly easily, especially if you recognize that 81 is actually a power of 3. And if it's not obvious, well, you should know that 81 is 9 times 9, right? It's 9 squared. But 9 is also a power of 3, right? 9 is 3 times 3. So it's 3 squared squared. In other words, it's just 3 to the power 2 times 2. It's 3 to the power 4. Right? But there you go. If 81 is 3 to the power 4, then what's the exponent, right? What does x have to be here? We have no choice, right? It has to be 4. Right? In other words, if 3 to the x is equal to 3 to the 4, as long as the bases are the same here, the exponents have to be equal as well, right? So x is 4, right? And so that solves the equation, right? If you have 3 to the x equals 81, then you're going to get, x equals 4. And let me just make that abundantly clear here, right? So 3 to the x equals 81 gives you x equals 4. And you can check. If I take 3 to the 4th power, right, that's 3 times 3 times 3 times 3 times. So I get 9 times 3, which is 27, and 27 times 3 is 81. So, of course, that works, right? So 3 to the 4th equals 81. Okay, and that's the only solution, right? There's only one answer here, right? And that has to do with the fact that it's 1 to 1, right? You can't get two answers, otherwise this would not be true. B would. So because it's 1 to 1, you're only going to get one solution here. Okay, so how about another one? I'll make this one a little bit trickier. Well, I'm not gonna number these, but so this is how about 2 to the x minus 5 is equal to 64. Okay, so we want to solve for x here. So what does x have to be? Right. So the trick is to write 64 as some power of 2. Now, again, if this number were, say, 63 or 75, you might not be able to do this very easily, right? So 64 is 2 to what power, right? Well, if I take 2 squared, I get 4. If I take 2 to the 3, I get 8. 2 to the 4, 2 to the 4, I get 16. 2 to the 5, I get 32. And if I multiply by 2 again, 32 times 2 is 64. So it's 2 to the 6, right? So this question mark here should be 6. Okay. So how does that help me solve the original equation? Well, notice I have 2 to the x minus 5 equals 2 to the 6. Now that the bases are both equal, right? If the bases are equal, that means we know these exponents have to be equal as well. And if the exponents are equal, then you just get this equation. And I'll give you 5 seconds to solve it because it's just that easy. Okay, everyone get 11, right? You just add 5 to both sides. So 6 plus 5 is 11. And that's the solution, right? You can check. If I take 2 to the 11 minus 5, that's 2 to the 6, and 2 to the 6 is indeed 64, as we already knew, right? So yes, x is going to be 11 here. Okay. So again, these are just very simple equations that we can solve using the fact that that the exponential function is 1 to 1. In other words, we're using this fact here, which I wrote down over here somewhere. Yep, right here, right? Yes, right here. So yeah, if all this says is that when the bases are equal, the exponents are equal as well, right? It's just a fancy way to say that b to the x is a 1 to 1 function. Okay. So yeah, so those are again simple exponential equations. Oh, let's do this one. Let's do a hard one. 2 to the 2x plus 3 equals 8 to the x minus 2. Okay, so I just needed some space. So it's 2 to the 2x plus 3 is equal to 8 to the x minus 2. All right, and this is probably about as hard as I would make it, at least for this section. You know, we'll solve some harder ones later. All right, so the one thing you have to be careful of is that the bases are not equal, right? 2 does not equal 8. So it's not like we can say that these two exponents are equal, okay? But on the other hand, this 8 is also just 2 to the power 3, right? 2 times 2 times 2 is 8. But now this 8 has an exponent of x minus 2, right? And by the properties of exponents, right, you take 2 to the power 3 to the power x minus 2, and that's just 2 to the power 3 times x minus 2, right? And if you expand that out, you just get 2 to the power 3x minus 6. So by manipulating the exponents like this and just simplifying a little bit, notice that the left side is 2 to the power 2x plus 3. Right? So I just copied that down here, right? So the whole point for that is now, notice the bases are equal, right? B equals B, 2 equals 2. Now we can say that this exponent has to equal this exponent here. Right? So now we just have to solve this equation here. And this time I'll give you 10 seconds to solve this. Yeah, right. So just take away the 3x from both sides. Although you could have taken away the 2x too, because you get negative x plus 3 is equal to negative 6. So now take away 3 from both sides, and you end up with negative x equals negative 9. So divide by negative 1, and you get x is positive 9. Okay, so that should solve the original equation, this one here. And I'll leave it to you to check, but I'm pretty sure it's correct. So yeah, here the exponent's 21. Here it's 7. 7 times 3 is 21. Yeah, I think it works. Okay. So yeah, so all exponential functions are 1-to-1, which means that if the bases are equal, right, if these are equal, then the exponents have to be equal as well. So keep that in mind. Right. Next thing I want to do is just talk a little bit about this number e. So lowercase e is a number, or it represents a number, and that number is approximately 2.71828. And if you really want more digits, right, it's like pi. It just keeps going forever. So here's, I don't know, 20 or 30 digits. Obviously, we don't need that many. In fact, if you notice, it is in your calculators, in your graphing calculators, if you just do second, the second key, which is like the shift key in the upper left, and then I think it's the division symbol. I think that gives you the e, which, in your calculator is 2.718281828. On the other hand, there's another way to get e on your calculator. And so the other way is to do, again, the same shift key, the second key on the top left, and then you hit the button that says ln. Now, where's the ln? I think it's just to the left of either 4 or 7, right? Not the one that says log, the one that says ln. So it's on the left, right? And what that gives you is e and then an exponent, right? So on my calculator, it has a little caret for the exponent. On your calculator, it probably just has a little box here saying, okay, what's the exponent now? So if you just put the exponent of 1, right, e to the 1 is just e, and it'll spit out the same answer. But something that we're going to do a lot of is use e as the base. In other words, right, you're going to have a function e to the power x. So very often, right, we're going to see this function a lot, e raised to a power. So in this case, it's 1, but you can use x equals 2, 3, 4, negative 18, whatever, right? So you're taking the base, this e is this number here, raised to the power x, okay? Now, if you're wondering where does this number come from, well, that's a very long story, and not one that I think most of you are going to really care that much about at this point. If you are really interested, you can just Google it, look it up, right? It's the e, I think, comes from Euler, and I don't know if that's why it's given the letter e. But if you look up Euler's number or this number e, that should give you the whole story of where this comes from. And it's basically from calculus, so let's not get too deep into that. For our purposes, it's just a number. And it's the base of this exponential function, e to the x, right? So for our purposes, it's going to be a base of an exponential function. Right. And so why do we care about these exponential functions? Well, they turn out to be fairly useful for computing various things. And one of the examples we're going to look at very carefully here is the idea of compound interest, right? So when you stick money in a bank, in a savings account, let's say, or any type of investment account, usually you get either interest or some rate of return. Let's say it's a savings account, you just get interest, right? So that interest is compounded every so often, typically every day. In some cases, it's compounded, even more often, like continuously. And if it's compounded continuously, you're using this formula. If it's compounded n times a year, you use this formula. This one here on the left, right? So don't spend any time memorizing these, because if you need these formulas, we would just give these to you, right? Or you can look them up, of course, on a test now that they're online. So you can have these formulas in front of you. But here's the idea, right? So all these different letters represent something. So I'm going to scroll down and just copy it down here, because I think I remember it. So you have the formula A is the amount of money, is equal to P times, and then in parentheses, 1 plus R over N, all raised to the power N times T. And in particular, we're going to think about this as a function of T. And if you notice T is in the exponent, that's why this is an exponential function. right? So it is exponential in both t and n, although we're primarily concerned with t here, right? So let's get to what this means here, right? P, let's start with P. P is sometimes called the principal, right? Or present value. So it's just the amount of money that you're starting with, right? How much are we starting with here, right? Right. So P is just some amount of money, you know. Oh, let's do an example. Let's say we start with, I don't know, $5,000. Right. That'd be nice, but let's suppose we have $5,000 and we're going to stick it in a savings account, right? All right. R is the interest rate. I should be maybe a little more specific, right? It's the annual interest rate, or sometimes called, it's the annual nominal interest rate, right? Right. So it might be, for example, how about 3%, right? So if if the interest rate is 3%, be careful, R is not 3. R is a decimal, 0.03. So don't forget to convert your percents to decimals. Okay. N is the number of times we compound each year. It's the number of compounding periods. We compound per year. Okay. Right. And that makes T just the number of years. It's the time in years. Right. Okay. So let's suppose we compound, let's do monthly, right? We compound every month, right? So there's 12 months in a year, which means n is 12, right? If we're compounding daily, n would be, 365 in a non-leap year, right? But let's stick with 12. 12 months in a year, we're compounding every month, right? So how much money would we have after, let's say, 7 years, right? So A, then, is that amount of money. A is the amount of money after t years. After t years. Okay, so we just calculate all this. So let's do that here. So the amount of money we're going to get is going to be P, which is 5,000, times 1 plus R, R is 0.03, divided by N, right? N was 12. And then the exponent is going to be N times T. So N is 12, right? 12 times T, and T is 7. So 12 times 7, right? So what is all this, right? Well, we know 12 times 7 is 84, so that's the exponent here. But let's calculate everything else first, right? So 0.03 divided by 12, 0.03 divided by 12 is 0.0025. So this is 1 plus 0.0025, right? 1.0025. So that's the base, and then the exponent was 84, I think. All right, so I would not try to do this by hand. This is why we have a calculator. So if you plug this in your calculator, what do you get? So I get, again, this is in dollars now, $6,166.77. Yeah, I think that's it. I'm just double checking here, right? So, so you start with $5,000, and after 7 years, I know that's a long time to wait, you're going to have $6,166.77, right? And from that, we know that, right, when you subtract, you get $1,166.77 from your original $5,000, right? So this is just the interest. This is just the interest, right? And that may not seem like a lot for 7 years, but keep in mind the interest rate is only 3%, right? So that's not going to give you a whole lot of money here, right? Even though 7 years seems like a long time, right? And so, you know, if you remember, the exponential functions generally grow quickly, right? So remember, the graph went very quickly. It went like this, right? And if you're thinking, well, this doesn't look like your money is growing very quickly, remember, the exponential function over here on the left is actually very flat. So we're thinking about what's happening here because of the very low interest rate, right? Your money is growing very, very slowly at first. Very slowly, right? But if you wait long enough, eventually it will grow very quickly. You might have to wait a long time, right? Obviously a lot more than 7 years, right? And let's do 70 years, right? Let's do the same calculation, just change t to 70, and let's see what we get, right? So I'll write this down again. So suppose t is now 70 years. You'll see you get a little bit more money. So 5,000 times 1.0025 to the, well, 12 times 70 is 840. So a much bigger exponent. And so, I'm just going to do it here. Give me a second. So 1.0025 to the power 840. And then times 5,000. So after 70 years, you're going to get $40,723.99. Okay, from $5,000. So that's a big increase, but again, who's going to be around 70 years from now, right? Well, you might be, but probably not. So that's a fairly long time. And if you really want to be, you know, exaggerate this completely, you can do 700 years as well. And if you just give me a second, I'll do that. Hang on, I messed up. Give me one more second here. Sorry about that. The power. Okay, yep, you do get a lot more money if you're lucky enough to wait around for 700 years. Hang on. So, yep, in other words, if you plug in 700, you end up with basically $6 trillion. No one's going to be worried about pennies at this point here. But, oh, sorry, that's not a comma. That's a decimal. 39 cents. Yeah, million, billion, trillion. So yeah, $6 trillion. Now, of course, 700 years from now, $6 trillion might not get you very much, but that shows the exponential growth here, right? Eventually, you will see this explode. It'll get very bigger, but you got to wait a long time before that happens, right? So that's the power of exponential functions, right? And we can simplify this if we go back to this formula, the p e to the rt. That's when you're compounding continuously, right? So n is the number of times you compound a year, unless you're compounding continuously. If you're compounding continuously, then, well, you're compounding every moment in time. And since there's an infinite number of moments, n is really, n behaves like infinity here. But since infinity is not a number, you can't just plug it in here. That's why you have to use this formula here. So let me write that down. Right, when you're compounding continuously, you're using this formula instead, right? And it's a slightly simpler formula, right? And so let's sort of do the same example here, right? P was still, let's say P is still $5,000. That's what we're starting with. Let's say the interest rate is still 3%, right? And let's suppose we wait 7 years, right? How much money do we have if we're compounding continuously? So plug in the numbers. The amount of money will be 5,000 times e to the power 0.03 times 7, which is 5,000 times e to the 0.21, I think. Yeah. So plug all that in your calculator. Yep. Right, and I come up with the grand total of $6,168.39. Right. Compare that with when you're compounding monthly, where we only get $6,166.77. So by compounding continuously, sure, you get more money. What do you get? You get a couple bucks, right? Not even. It's like $1.60 or something, $1.70. So yes, compounding continuously sounds like you should make a lot more money. You make very little more than compounding monthly or daily, for example. Then daily would be somewhere in between these. And yeah, you're talking about pennies or maybe a few bucks. So effectively, you know, the changing to compound continuously here doesn't give you that much more money. You know, and it's also a good way to approximate when you're compounding, say, you know, every month or every day. This might, you know, if you use this formula, you know, instead, yes, it's still approximate, and you might get a little more than what it should be. So if you approximate using this formula, then, you know, maybe subtract off a few pennies or a few bucks, and you'll be pretty close. Okay, so I think we can do one more example here. I'm calling this example 11 because that's what it says in my notes, but that's probably not the 11th example we did yet. So the question just says, so you have the amount of carbon-14 in grams, right, after t years is given by this formula here. And if it's not clear, let me write down the given formula. So, right, so this is given. It's a of t, so a is a function of time. That's the amount of carbon-14, is 285.00 times, right, 2 to the power negative t over 5,750. Right. So yeah, the exponent is a fraction like this, and that's what happens when you have a fraction in the exponent. You might want to conserve space here. Okay, so that's given, right? And so we want to find the amount of carbon-14 after, let's say, 0 years. So in other words, we just want to evaluate this function at t equals 0. So if t is 0, you just get 285 times 2 to the power 0, right? And 0 divided by 5715 is still 0, and negative 0 is still 0, right? Well, remember, 2 to the 0 is not 0, right? It's 1. So you just get 285 grams. Well, that should not be a surprise, right? The 285 grams, that's how much we're starting out with. So right now we have 285 grams of carbon-14. Carbon-14. So it's an isotope of carbon. Okay. And this is going to come up in more examples later because this has to do with carbon dating. So if you find a fossil and you want to know how old it is, typically they're going to use carbon-14. They're going to measure how much carbon-14 there is in relation to carbon-12. And by that measure, you can figure out roughly how old that fossil is. So that's where this comes in very useful here. So again, that was part A. Part B, we want 100 years. So how much carbon-14 will there be after 100 years? So it's still 285, but this time it's going to be times 2 to the power negative 100 over 5715. So now we got to calculate this a little more carefully, right? So 285, and then what's in the parentheses? So again, this is something you're going to need a calculator for. So we have 100 divided by 5715. And maybe I should write that down, right? So this is going to be 2 to the power negative 0.0174978113, and so on. Yeah, don't round too much here. You should keep as many decimals as your calculator allows for. Right. Now, what happens when we take 2 to that exponent? Well, all right, I got to use my calculator. Give me a second. Okay, so 2 to that power is roughly 0.98794. Close enough. So now, well, maybe not close enough. 7945, let's say. So now when we multiply that times 285, we get 281.56. Sorry, that's a 556 grams. Okay. Now, how did I know to round to 2 decimal places? Well, if you look at the original problem here, see, this was 285.00. I just forgot to write the 0.00 here, right? So the 0.00 tells us to round to 2 decimal places here, right? Okay, so yeah, we have 285 grams now. In 100 years, there's only going to be 281.56 grams left. So we lost a couple of grams. You might wonder, where did they go? And that's a physics problem. Essentially, the carbon-14 isotope is what's called radioactive. It's unstable, which means that it emits these little particles, these little protons and neutrons, or I think helium nuclei and electrons and things like that fly off. That's radiation, right? So that's what radiation is. It's just very high energy particles like electrons or high energy electromagnetic radiation, right? So that's what's happening. It's it's invisible, right? We can't see it, but we know it's there. You can measure it with the Geiger counter and so on. And so, right, so it takes about 100 years to lose just barely 3.5 grams or so, right, in those particles. So what happens after 1,000 years? So part C, we want 1,000 years now. So you just do the same thing. You just change the exponent here for part C. So after 1,000 years, you still have 285, right? Times 2 to the negative 1,000 divided by 5715. And you calculate that. And give me a second. Get 252.45. Oh, hang on. Let's write that down. 252.45 grams. So yeah, now we've lost not quite 30 grams or so, 20, 28, 29 grams, right? Okay. I think that's right. I'm just a little surprised, but I think that's correct. Right. And what happens after 5,715 years? So exactly 5,715 years. Well, you still get 285 times 2 to the negative 1, basically, right? So 5715 divided by 5715 is just 1. So this is just 2 to the negative 1. And 2 to the negative 1 is 1/2. So you get 285 divided by 2, which is 142.5. So 142.50 grams. I think that's right, yeah. Although let me double check. Yep, I think that's right. 142.5 grams. And I'll let you plug in the 15,000, right? So obviously the longer you wait, the less you have. Oops. Sorry, it should be 10,000, I think it was. Oh, I'm sorry, 15,000 years. Okay, 15,000 years. Divided by 5715. So again, these are all approximate, by the way, but you know, close enough. All right, so plug that in your calculators. All right, everyone got it? I get 46.12 grams. So very little left, right? Compared to the 285 that we originally have, right? But this is what happens after time. All the radioactivity over those 15,000 years means that you have less remaining. And yeah, so in terms of the graph, what's going on here? You want a picture of it? So here's t. Originally we started at time t equals 0, way up here. This is 285 grams. And over time, this is going to decrease. Now, at first, it's going to decrease rather slowly, right? But over time, you just get less and less, right? And until eventually there's nothing left. But you know, you might have to wait millions and billions of years for that, right? So this is also an exponential function. Remember, this is what happens when you have a decreasing exponential function, right? In other words, you can think of this either with a negative exponent or where the base is 1/2, right? So another way we could have written this formula here is a of t is equal to 285 times 1/2 to the power t over 5715 without a minus sign, right? Here it's a plus sign. So same thing as the formula they gave us originally. So that's how this goes, right? In most of the problems, they give you the exponential function, and you simply have to plug in various numbers for the exponent, right? Different exponents give you different values. And I hope that helps.